And it makes sense that we should get the exact same thing, offsetting a plus or minus there. So if I look at this equation right here, questions before we actually show how they're, indeed, we get to use the same answer. Any questions? There's an electric pencil sharpener on the counter over there.
Oh, okay. Hopefully this doesn't disrupt anyone. Thank you.
So if I look at this one, if I take the square root of both sides, I get VF is equal to the square root, that's an F there, VF equals the square root of K delta X squared over M, delta X initial, which is equal to the square root of K over M times delta X initial, which is square root of K over M times my amplitude, because I started out with it stretched all the way out when I let go, and square root of K over M is just omega. And that's what we had in front of our velocity, generic velocity equation, ignoring the negative sign. Because energy just doesn't tell you velocity, it tells you speed. And so it better be a positive number. But a second way of doing the exact same thing. All right, any questions before we go to vertical springs? Yeah, all right, that's the excitement I want to see.
I'm rejoicing on the inside. I'm rejoicing on the inside.
Oh, absolutely, we all do. Like physics humor generally makes you laugh on the inside, rarely on the outside.
That Pascal joke was a pretty good one.
All right, so I have a spring, just some natural length to it. I then add a mass to it, and this is some value of, we'll call this x1. When I add the value to it, it now stretches down an additional x2. So the total length of the spring is x1 plus x2. And then I pull it down, the same mass, I pull it down past equilibrium and I let go. So this thing's gonna now oscillate back and forth. The distance that I pull it down now is an additional x3. So when I'm applying Hooke's law, if I want to find the acceleration at that point, how do I go about that?
You have to determine all of the forces that are acting on it.
All right, so at that point right there, I pull it down there, I let go. What are all the forces acting on it as soon as I let go?
The elastic force pulling it up. The force of gravity pulling it down.
Anything else?
Force of mass.
Not a thing.
Yeah. Oh wait, the force pulling down. That was pulling down on it.
Yeah, but motion has no memory. It has no idea about that because I have to let go when the problem starts.
The potential energy.
Looking for forces right now. We'll bring potential energy into it later, but not yet. You're just ahead of your time.
Right. That's all the forces that are.
Okay, yeah, that's it.
Oh.
It's not in equilibrium. So we have this spring force, so let's assume up is positive, because I think we can pretty much be sure it's going to accelerate upwards. Fs minus the weight is equal to mass times acceleration. The spring force is equal to the K times the stretch. just write delta x for right now, minus mg is equal to ma. We know from this middle situation right here, we know what delta x is, or we can find it, because here we also have the spring force acting up and weight acting down, but this is in equilibrium, and so they will balance each other out. K times, how much is this thing stretched?
X2.
X2.
Yep. Kx2 is equal to mg, so K is mg over x2. So we now have the value for K here. Mg over x2 times delta x minus mg equals ma. But the question is still, what is delta x?
Delta x from equilibrium with the mass on it, dx3.
Hooke's law, delta x is how far it's stretched.
X2 plus X3.
It is x2 plus x3. You can get away with what you just said, but we have to take something else. We have to consider something else. So this becomes mg over x2 times x2 plus x3 minus mg equals ma. We distribute, because that's tradition. So we have mg over x2 times x2 plus mg x3 over x2 minus mg equals ma. We can cancel some stuff out now, which is just darn convenient. And so over my first term here is just mg, but I got a minus mg here. And so those cancel out, and what I'm left with is mg x3 over x2 is equal to ma. All right, so if we are bringing the weight into it, if we're bringing the gravitational force into it, then the spring, the stretch of the spring has to be from that position right here. However, if we ignore the weight, because weight has disappeared here, then we only really have to consider it from here. And it basically is the same problem as the horizontal spring oscillating back and forth. It's just now vertical. The question is of how far you consider the stretch. So stretch from, because this x2 has the weight built into it. So if we're bringing weight in here, we have to take that into account. If we want to ignore weight, as was suggested, then, or want to make the stretch just x3, then we ignore weight in the problem because it canceled out. This right here, this mg over x2, that's just the spring constant. So this becomes kx3 is equal to mass times acceleration. And now as it oscillates up and down, we see that we have a Hooke's law variation for it right there. And so therefore, if I take a spring with K equal to, let's say 24.5 newtons per meter, and I have a 4 kilogram mass sitting on it, it has some natural stretch to it. I then pull it down 2 meters and I let go. What's my equation for position, velocity, acceleration? What's my maximum velocity? What's my maximum acceleration? What is the period, and so forth and so on? It's the exact same problem that we just did. As long as we consider just the 2 meters and not how far that stretched it. If we consider how far that stretched it, then we have to make some adjustments. Although maximum speed should still end up being the same. Maximum acceleration would still be the same. And that's the vertical. Questions? Okay. All right, we'll see how far we can stretch this thing. Or, no pun intended. Yeah, we'll do this and then we'll do the,
We got a half hour.
yeah, we got loads of time. All right, so I got a mass hanging from a string. And I'm gonna pull this back and I'm gonna let go. So this thing is, basically, it's a pendulum.
Yeah.
All right, so the dotted line represents sort of that natural hanging length, and I pull it up to here. And I let go. So it's gonna go in that direction. Let's think about the forces. What are the forces acting on the mass here?
Force of gravity,
All right,
force of tension. And that's it.
okay. Which way will it accelerate? I pull it out to here, I let go. Which way will it accelerate at that moment?
Down and to the right.
Okay, basically that direction right there.
Yes, yes.
So since that's gonna be my direction of acceleration, I wanna break my vectors up so that they are either parallel or perpendicular to this. Well, tension's already perpendicular to it, so I don't need to break that up. So I'm gonna break weight up, so let's introduce a variable here, theta.
What is that next to the A?
What is this?
Yeah,
That's an arrow.
oh,
Direction of acceleration that way. That angle there is theta, which means that angle there is theta. So I'm breaking weight up. I have weight acting down. And then my perpendicular components, where this angle here is theta, just basically looking at this triangle right here. Except drawing it bigger. What is the magnitude of this side right here?
Cosine of theta weight.
Yep. So this is W times the cosine of theta. And this side?
W sine theta.
So I'm claiming that my force diagram here, where I got tension and weight acting down and tension acting up at that angle, I can rewrite that as I've got tension acting up at that angle. I've got W cosine theta acting opposite, and W sine theta acting perpendicular to it. All right, so now testing those memories again. In what direction will the acceleration be? We said it's acting, I guess we did say it was acting this way. There are actually two types of acceleration involved here. What are the two types of acceleration involved?
One acceleration should go to the center of the circle.
What is that acceleration called? Yep.
Centripetal.
Yes.
So we have a centripetal acceleration. This acceleration right here, this is actually the tangential acceleration. I should put a T there. And then there's a centripetal acceleration acting that way. We actually don't care about the centripetal. I just want you to remember that it's there. So let's look at the tangential acceleration. I know F equals ma. The force acting on it is W sine of theta, and that's equal to the mass times my tangential acceleration. Now there is a small problem here. One that I usually get to near the end of this derivation, and then I go, oh, I forgot, and then I go back and add it. But hopefully we're catching it this time. So this is, theta is 0 degrees when it's down like this. When I pull it that way, is that positive theta or negative theta?
Negative.
You want to make that negative?
Yes.
Okay. So that theta then, this becomes the sign of negative theta. And what's the sign of a negative angle? What is the sign of negative theta? If it helps, sine is an odd function as opposed to an even function. I don't know if that terminology is stuff that you've used before. All right, what's the cosine of negative 30 degrees? Sorry, a sine. What's the sine of negative 30 degrees?
The sine of negative theta, that's a 0.
What?
That's what, when I put it in the calculator,
Yeah, but we don't actually have a value for theta.
Oh, that's a 0 there, I think. Instead of theta.
Oh.
Sine of negative 30 degrees?
Negative 0.5.
Okay. Sine of negative 30 degrees is negative 0.5. What's the sine of 30 degrees?
5.
0.5.
So what's the sine of negative theta?
Is theta.
Negative. The negative number.
Right. Sorry, I heard parts of it, and it could be I just missed it because the siren was going by.
Oh, I just said it was a negative number.
Okay, it is, well, it depends on what theta is. I was looking for something more generic. Sine of negative theta is the negative sine of theta. That's what I was going to shoot for. That's the basics of any odd function, the sine, so f of x is a odd function if the f of negative x is equal to negative f of x. That's odd function. And then an even function would be f of negative x is equal to f of x. That's an even function. So this negative sign here, we can just pull that straight out. Negative w, well, we know what w equals. Negative mg sine theta equals ma. N cancels out. All right, so we're almost there. Rotational motion. Flashback to rotational motion. I have a circle here, some arc length, S, R, and theta. What's the relationship between S, R, and theta? If theta is in radians. From the silence, I'm guessing you don't remember.
Yeah, I don't.
I was thinking we did this last Wednesday, or maybe I did that with a different group.
I'll admit I have some trouble recalling this stuff.
If I take a circle, this part I'm pretty sure we feel more confident we actually did this part. If I take a circle with radius r and then I take that r and I wrap it around the side here, what is that angle?
Radian.
1 radian.
Yeah. If I wrap two r's around here, what's the angle?
3 radians.
So what's the relationship between this length right here, this radius, and that angle?
It is, 1/3. Like, oh, it's, S is, S is 2/pi?
No. That, I'm not sure where 2 and pi show up, in my generic equation here.
Oh,
The theta equal S over R.
Yeah. So the angle is whatever that length is right there, divided by the radius. So if this is 2r, that's 2 radians, because 2r divided by r is 2, and so on. Or S is equal to r times theta. So if I have a wheel that is rolling perfectly, a perfect roll, then the angle that the tire will go through is equal to how much of the tire touches the road as it's going, divided by the radius of the tire. Again, assuming that the tire doesn't flex or anything like that, or just perfectly rigid circle and no slipping. So this is the distance that actually travels. This is a distance is equal to the radius times the angle it goes through. If I take the derivative with respect to time, ds dt is equal to r is a constant, so r d theta dt. What is the derivative of the distance an object moves with respect to time?
Velocity.
Pardon?
Velocity.
Technically distance, so not
Speed.
velocity.
Speed.
Yeah, speed. And then the change in the derivative of the angle with respect to time?
I mean, all I know is angular velocity, but if it's not a velocity, well, it would be a velocity.
No, it's not velocity, it's the other one.
It's an angular,
Angular,
something like that.
It's angular speed?
angular speed.
Oh,
Yeah, angular speed.
Never heard that term before.
Do you remember what the symbol for angular speed is?
new?
Didn't we say it was that funny B?
Oh, no, that was frequency.
Oh, okay.
It's the funny W, it's the omega.
Oh, okay.
It is the exact same symbol that we use for angular frequency. Matter of fact, the units for angular speed and the units for angular frequency are exactly the same thing.
Radian per second.
Ready? Yep. I have not seen any case where you really need to make a distinction. There's a philosophical difference between angular frequency and angular speed. However, mathematically, you can treat them as the same.
I don't think I've ever heard it called angular speed. I've only ever heard angular velocity.
Angular velocity would have a specific, you care about the direction, angular speed doesn't, that's the difference.
Okay.
If we take the derivative again, so dv dt is equal to r d omega dt. What is the derivative of speed with respect to time?
Is it still called acceleration?
It is.
Okay.
If you wanted to throw something in front of that, it's linear acceleration or translational acceleration, but I think habit is, if you say acceleration, we mean the linear one. And what is the derivative of angular speed with respect to time?
Angular acceleration.
Yep, and what's the symbol? This is where they get all fancy and they go, let's see, acceleration starts with an A, but we're doing angular stuff, so let's come up with a Greek letter that starts with the letter A.
Alpha.
Yep. So A equals R alpha. This is tangential acceleration is equal to the radius times the angular acceleration. So we can now come over here, and this is equal to R times alpha. R is the radius of the curvature. In other words, R is this distance right here, which I'm going to label as L, because traditionally textbooks use the letter L. Actually, I'm going to use a lowercase l. So what I've basically taken my equation down to is negative g sine theta is equal to L times alpha. We gotta do one more thing, and then we are ready to connect it to the stuff that we've been doing, to Hooke's law. Have we discussed small angle approximation in this group?
I thought we mentioned it.
Briefly.
Yeah,
Okay.
you briefly mentioned it.
So, if theta is small, what's true?
Then the sine of theta is very close to theta.
Which is very close to. Okay, I might not have mentioned the other part. It's also very close to the tangent of theta. They're all very similar, as long as we're dealing with radians here and theta is small. So if we assume that our angle, that we have this thing and we pull it back just slightly, not very far, just pull it back slightly, then my equation down there becomes negative g theta is equal to L times alpha. And you might be looking at that and going, well, it's obvious what's next. Or you might be looking at it and going, wait a second, how does this connect to Hooke's law? So let's assume that you don't see it immediately. Hooke's law is negative k delta x is equal to mass times acceleration. I suspect there's something wrong with my car warranty. Notice the parallel here.
Oh.
Remember that acceleration here is the second derivative of my displacement. My angular acceleration is the second derivative of my angle. So we don't have to do any more math here. We could go through the whole bit that we went through before, or we could just take advantage of what we've done. So if the period was, let's start out with omega. No, start with period. So if the period is 2 pi times the square root of m over k, that's what we derived already. Well, if I'm dealing with a simple pendulum, then the period is equal to 2 pi times the square root of, well, m parallels with L, and k parallels with G. That is the period of a simple pendulum. And we can actually test that out. So let's test it out. Do all of you have a stopwatch on your phones?
Yeah, let me just get mine, clock. Okay, I've got a stopwatch.
There.
Stopwatch is ready. Okay.
I really don't want that here, so put that over there. How much is this going to mess it up? I'm going to shorten that a little bit. All right, so basically I'm going to pull it back a little bit and swing it back and forth. I want you to measure how long it takes to do 10 oscillations. So I'm going to do 3, 2, 1, go. When I say go, I'm going to let go of it, and then we'll count 10 oscillations.
All right, let me just move over some.
Okay. And I'm going to move this into the camera.
Looks like you may want to shorten it. It's
It's a little bit off.
yeah, it's a little off.
What do
I can see the hook. There we go. Like,
All right, that's going to have to be good enough. All right, there we go. 3, 2, 1, go.
okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
16 seconds and 53 milliseconds.
Dang, I got
So just a second, so 16.53.
16.6.
Holden, you said 16.53?
Yes, that is. Yeah, that's what I got on my stopwatch.
And Aaron? Yeah.
Yeah, I got 16.6. I was a little bit slower on
I got 16.54.
I don't have.
Okay, all right. So let's assume that we've done this correctly. I did it 10 times because if I found that under a half a second, reflexes really start to play a major role. But obviously, the more we can eliminate reflexes, the better it's going to be. Let's see, so the average of these three things is, let's see, that's 1, 7, 8 divided by 3 is 2.6.
16.55. Or 5.6, or rounded, yeah.
I assume 5, 5, 6 repeating.
Yeah, yeah. Do you do that in your head, or?
Yeah, that one I did.
Okay.
There are only 3 numbers I basically established that as my base. That's 1 ahead of it.
Mm-hmm.
That's 7 ahead of it. So now I'm just doing 8 divided by 3
Oh,
and adding to
okay.
that.
That's impressive.
Part of it is I was not allowed to use a calculator in any math class till I got to calculus. So I had to come up with ways of dealing with some of it.
Yeah, that helps. Yeah, that sounds like it helps.
All right. So therefore the period, the experimental period, that was 10 oscillations, so the period is just 1, so I divide by 10, so 1.6556 repeating. I take it out that many decimal places, like we're gonna match that close, but let's pretend that we are. The acceleration due to gravity in Winston-Salem
9.798.
Pardon?
Is it 9.798?
Yep. And L, notice that the mass is not part of the equation, the mass has dropped out, so that does not affect. So we need to measure that distance. So technically, when we're doing our simple pendulum, we are assuming all the mass is concentrated in a single spot. Now this is not, the string does have mass, and this is not a point mass, it does have some depth to it, or thickness to it. So what I'm going to do is measure from the pendulum to what I'm going to estimate is